We talked about the Argand diagram and how we can represent a complex number on the Argand diagram. And another advantage of this is we can use another way of naming coordinates. Instead of using the traditional x and y, we can put it in what we call Mod-Arg form, or when it's the number plane, it's actually known as polar form. You might see it somewhere written as polar form. First thing, mod stands for modulus. Modulus, again, is something you've been dealing with and you just didn't realise it. It's basically the length of the vector, and we'll talk more about vectors later, OZ. So if I place a complex number on there it is z equals x plus iy. The vector OZ is simply the line. That'll do us for now until we talk about vectors in a bit more detail. The line that joins the origin to that complex number. The length of that is the modulus. And so of course I could use Pythagoras' theorem. I know it's the square root of the real part squared plus the imaginary part squared. And you remember all those times when I said, oh, the difference of two squares becomes the sum of two squares, so it's x squared plus y squared, the real part squared plus the imaginary part squared. And I said, oh, this will become more important later. This is why it's such an important thing. It ties in with this modulus, because of course, to find it, that distance, sometimes we symbolise it with r for modulus. R for modulus, anyway. Square root of x squared plus y squared, just the distance formula. Its symbol, you'll notice, is the absolute value signs, because that is what absolute value actually is. Actually is modulus. And if you think about it, how was absolute value originally, I hope, originally introduced to you when you first saw absolute value? It's the distance of the point to the origin. We weren't worried about plus or minus. And so that's exactly what we're talking about here. It's still the distance to the origin. It's just now, it's not a horizontal distance necessarily. It could be going off at any angle. So the modulus of z is the square root of x squared plus y squared. Now, the other thing that would define this point, we've got the distance from the origin, but it's the angle that it makes with the positive x-axis, and we call that the argument. The argument. It ties in with trig if you think about it. You remember how sometimes we said slope of a line is tan theta, where theta was the angle it makes with the positive x-axis? So that angle is the argument. So there it is there. The theta symbolised simply ARG for arg, so we sometimes say argz. So it'd end up being, well, the inverse tan of y and x. Now, of course, there's an infinite number of possibilities, so we restrict our answers. When we're talking about the argument, we only want answers between pi and minus pi. Now, that makes it really easy, because if it's a positive, then I know it's above the axis. If it's a negative, I know it's below the axis. Now, yep.
Just ask me, why is it equals?
Because you can't have two answers for the same point. So if a point was over on the left-hand side here, yes, it's pi or 180 degrees, but it's also negative 180 degrees. We pick the positive one. So that's why pi is included, but negative pi is not included. So if it's on the axis, we'll use positive pi. But as I say, and we're dealing with either an acute angle, which we'll put it in the first quadrant, or if it's in the negative, it'll be the fourth quadrant, or an obtuse angle, which you'll put it, if it's positive, in the second quadrant. If it's negative, it'll be in the fourth quadrant. So if I want to find the modulus and the argument of 4 minus 4i, okay, well, the modulus is the distance to the origin, so the square root of the real part squared plus the imaginary part squared. So for this one, it's 4 root 2. The argument, the inverse tan of minus 4 and 4. Now, this is where we've got to be careful, because yes, that is minus 1. A calculator can only give you one answer. Okay? So it's important we know exactly where we're located. I know this is in the fourth quadrant because the real part is positive and the imaginary part is negative. Therefore, I'm looking for a negative acute angle. So when I go to my calculator, I think it actually does give the negative acute angle, so it's okay. Minus 45, but in radians. We like to use radians for this. So minus pi on 4 is the argument. So how do we actually express it? Everyone can be written in terms of its modulus and its argument. So yes, x plus iy is when it's in terms of its coordinates, if you like, the real and the imaginary part. Using a bit of trig, we can easily show that x would turn out to be the cosine, or r times the cosine of theta. And the y value would be r times the sine of theta. Obviously, r is the same for both, so we could factorise it, and we get r cos theta plus I sine theta. So, the Mod-Arg form of a complex number is that z equals r cos theta plus I sine theta. You will sometimes see it abbreviated like that. CIS. C-I-S. That's fine, but I'll tell you right now, mathematicians at a high level don't like the term cis. And so we write it as cos theta plus I sine theta. Because too many people look at it quickly and get it confused with cos theta. Right? So, but if you end up writing cis, it will be acceptable. Well, we'll take it. But it's what it is cos theta plus I sine theta. Where r is the modulus of z and theta is the argument of z. So back to our 4 minus 4i, that would become 4 root 2 cis minus pi on 4. Cis, by the way, if you haven't worked out, is cos plus I sine. Yeah. The angle won't change, so it doesn't matter that we didn't put an angle about the cos and the sine. So root 3 plus I, well, I'll find its modulus, square root of the real part squared plus the imaginary part squared. We get 2. And we get its argument, and that one turns out to be pi on 6. I knew that was in the first quadrant because they're both positive, so I didn't worry about drawing a diagram for that one. I knew it's an acute angle. So pi on 6, 30 degrees. So 2 cis, or 2 cos pi on 6, plus I sine pi on 6. If you had to convert back, then you really do need it in the other form. Because remember, what this is really meaning is 6 times the cosine of pi on 6 plus I times the sine of pi on 6. They're both exact values, pi on 6, of course, being 30 degrees. So 6 times root 3 on 2 plus a half I, expanding that. So 6 cis pi on 6 would be 3 root 3 plus 3i. Well, how do we play with it when it's in Mod-Arg form? How do we multiply, divide? What are the relationships? Okay. The modulus. If you've got 2 complex numbers, you want to multiply them together, it doesn't matter which order you do it in. You could multiply first, then find the modulus of the new number, or you could find the moduli, that's a plural of modulus, of both individual numbers and then multiply that together. You'll get the answer either way. Arguments, you'll notice, is a bit like log laws. When we multiply, we actually add the arguments. Okay? Multiply, we add the arguments. So another way of thinking about it is rotation. If we were plotting the number, remember, argument is the angle, so it's like how far we've turned the vector. So if I multiply it, I'm adding another angle on, so it's rotating, so on. And that's why, if you remember on Friday, I said multiplication by I was like rotating 90 degrees. Okay? Rotating 90 degrees. That's because cos of 90 plus I sine of 90 is I. So what you've actually done is you've added the argument of I on. Because the argument of I is cis pi on 2 or cis 90. And so that's why I end up rotation that way. That's why multiplication by -1 rotated at 180 degrees. Because if you went cos of 180 plus I sine of 180, that would work out to be negative 1. You've actually multiplied by negative 1. Going to prove this. Here we go. So I'll let Z1 be R1 cis theta 1, Z2 be R2 cis theta 2. And we're going to multiply them together. So I'm going to need to expand them out fully there. Well, the R1 times the R2 is easy. That's just R1, R2. But expanding that binomial, we got cos theta 1, cos theta 2, I sine theta 1, cos theta 2, I cos theta 1, sine theta. Let's group the real and imaginary together, and you'll notice something interesting. Look at the real part. Cos cos minus sine sine. That's familiar. And look at the sine part. Sine cos plus cos sine. So in fact, what we've got is the cos of theta 1 plus theta 2 plus the I of sine theta 1 plus theta 2. So when we multiply, we have ended up adding the angles. And so there's our proof. So sure enough, the modulus turned out to be R1, R2. So that's the same as just multiplying them together. Whereas the argument, where we added them, the actual arguments. Okay, so it follows that. That was just two numbers. If I've got several numbers to multiply together, I could just multiply each of the individual moduli together and find the new modulus of the new complex number. And with the arguments, I would just keep adding all the arguments together to get the new number. All right, we have a similar one for division. Again, doesn't matter which order you do it in. And with arguments, you would subtract the angle when you're dividing. Subtract, again, just like the logs. I won't prove it. It's a very similar proof to the last one. It turns out, oh, look, we end up with a difference of the angles. So if I have a mixture, if I wanted to find the modulus of Z1, Z2 divided by Z3, Z4, and I already knew the modulus of each of the individual bits, I don't need to work out the new number to find the modulus. I could just multiply the ones on top, multiply the ones on the bottom, and then divide them all. With the arguments, whichever ones are on the top of the fraction, I guess I'm saying plus. Whichever ones are on the bottom, I'm saying minus to work out the new argument. If I was just raising it to the power of n, well then it must be mod z to the power of n, because remember, mod z to the power of n, we're saying mod z times 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 z, however many. And we just said that's the same as going mod z times mod z times mod z times mod z. So we'll end up with mod z to the power of n. So in other words, we can, for want of a better word, factorise or pull the power out of the modulus. Whereas the argument, again, very much like the logs, the power would come to the front, just like it does when you say the log of, say, x squared becomes 2 log x. The argument of z squared would become 2 arg z. Because if we're saying the argument of z, we would add all the arguments. So we're saying arg z plus arg z plus arg z plus arg z. How many of them? Well, whatever the power was. So we've got n lots of arg z. So if I had to find the modulus in the argument of this expression, yes, I could go and actually work out what this number is and then find the modulus of the argument. But it's going to be a little bit quicker to just say, well, I'm going to find the modulus of each individual bit and then multiply and divide. So I don't actually have to work out what that number is. So what do we turn up with? Oh, that was nice. Look at that. Root 13 and root 26 just happens to cancel there. So we've got root 10 as the modulus of our new complex number. With the arguments, the ones on top will be positive, so I've got plus inverse tan over a fifth. You notice I've got this strange theory here of -1 on -2. That's just to remind me that I'm not in the first quadrant. I'm actually, well, where would that one be? That's third quadrant, is it, where they're both negative. So that will actually be a negative obtuse angle. Minus inverse tan of 2/3. Now, these are not exact values, so I'm actually going to go to degrees rather than radians. A little bit easier to add with when they're not exact numbers. So the first one's 11 degrees, 19. Say we're expecting an obtuse negative, so that's what it was, -153.26. And the last one we take away -33.41. So there it is in degrees. -175.48 would be the argument of our new complex number. If we wanted to work out its actual value, then we could say, well, we know it's r cos theta plus I sine theta. Work it out. Obviously not going to be a nice neat number when we look at that argument. Okay. So, picked out a few here. In Patel, we've got the evens in 4B. In 4C, 1 to 10, also the evens. And in our pseudo-Cambridge, 9, 11, 13, and so on in 1D.